Hello, hello. Well, actually, I should say, whoa there, stop sign. If you have not already gone through the narrated PowerPoints referring to inferential statistics with respect to regression, then you've taken a detour that you shouldn't have. You've jumped ahead to spoilers. You should hit stop. You should close this out. You should go back. You should do the regression. Do that first. It actually doesn't matter a ton, but I do think that the transition is actually a little smoother if you go from regression to this rather than this to regression. And so what is this? Well, we're going to talk about tests with qualitative data. So thus far, and here I'm talking about the regression that we just talked about, we can explore a relationship between any two quantitative, I should have bold-faced that word, quantitative variables. That's pretty powerful. We can look at potential relationships between how much time you study and the grade you get on an impending Math 121 exam. We could look at the relationship between the miles of a car and how much we would expect it to sell for, how much we might price it if we were to try to sell it ourselves. Yeah, sometimes statistics isn't always isn't always pretty. It's not always sunshine and rainbows. This is a study I worked on once back in my heyday, no pun intended. We might look at the relationship between the number of larval eggs in a horse's stool and the number of parasites in its stomach. I know, a little kind of grotesque, but useful, right? Because if horses have parasites, that's bad. You need to give them some sort of medicine, some sort of shot. The strength of that medicine is dictated by how severe the parasitic infection is, how many parasites are in there. Now we can't know how many parasites there are without killing the horse and cutting open its stomach, in which case what's the point in curing the horse? But what we could do, what was done by researchers as a real life study, is what they do is they take the horse's stool. I don't pity whoever person this job is, to go through that stool, to sift through it, find all the different larva eggs, count those eggs, right? And we might expect a relationship. Here's a nice review question. Positive or negative relationship, you think? Between the number of parasite eggs in a horse's stool and the number of parasites living in its stomach. Yeah, I would expect a positive relationship as well. Now that's pretty cool, but what about, there's still a whole other realm of interesting situations that are being neglected, correct? And what are these situations? Well, what if we have qualitative data? There's a lot of really interesting questions that we as researchers could ask that involve not quantitative data, but rather qualitative data. As just one example, what if we wanted to explore the relationship between religious conviction, and we put that into three categories, and political affiliation, Democrat, Republican, Independent? What if we're interested in judicial outcome and race of defendant? What about judicial outcome and race of the victim? And I'm sure that if you really put your mind to it, you can come with many other examples, right? These particular examples, our regression techniques fall short. They can't get the job done. We need something more, and that something more is what we're getting ready to talk about. The type of statistical technique typically used to answer questions like this is called a chi-square test. It's talked about sometimes as two different types of tests, and there's sort of like conceptual differences, but actually all the computations end up being the same, and the p-values end up being the same, so the conclusions end up being the same. The idea of a chi-square test of independence is asking the question, right, are these two variables dependent or independent of one another? Does a person's religious conviction depend upon their political affiliation. The idea test of homogeneity is sort of looking at different groups. So, for example, maybe different political groups, Democrat, Republican, and Independent, and then looking at the patterns of probability within each group. So for a Democrat, what proportion of Democrats are low religious conviction, what percent are medium religious conviction, what percent are high religious conviction, and saying, is this pattern homogeneous amongst the political groups? Just a fancy way of saying, right, is it the same pattern of probabilities for Democrats as it is for Republicans, as it is for independents? Those chi-square tests are not particularly challenging to do, and they're incredibly useful. They're part of a course we might refer to as categorical analysis, right? Categorical variables, just another word for, we were calling them qualitative variables way back at the beginning of this course. But we just don't have that much time, right? Our time together is drawing to a close, bittersweet as it may be. So we're going to focus on a slightly simplified version of it to at least get a flavor of working with these qualitative variables, and in particular doing statistical inference, in particular hypothesis testing with respect to this. So the simplified version is something referred to as a goodness of fit test. And the goodness of fit test could be used to see whether or not a particular qualitative variable, so here we're focusing on just a single qualitative variable, whether it follows some pre-specified probability distribution. So we have some variable, it has a number of categories, we have a hypothesis that a certain percentage of the sample should fall into each of these categories. That may or may not be what happens. And so we have a way of conducting a hypothesis test to see how consistent or inconsistent is our sample from our hypothesized probability distribution. There's lots of really great uses of this, but maybe the most easy one to see, the sort of most basic beginner's example, is if you were a casino in which gambling is your bread and butter. And so everything in there you want to make sure is by the books, is fair. So if you're using a six-sided die to play whatever games there are that are played with six-sided die, craps maybe, you want to make sure that six-sided die is fair. What do we mean by fair? We mean that it's just as likely to get a 1 as it is a 2, as a 3, as a 4. You have a 1 in 6 chance of getting any one of those 6 outcomes. So this is really done all the time in these manufacturing plants as part of quality control. You take some dice, you pick them out of the manufacturing line, and you roll them. Probably more than 60 times, but right, to keep our numbers easy to work with, to keep them tractable, let's just say we did it 60 times. And let's say we got 12 1s, 7 2s, 14 3s, 15 4s, 4 5s, and 8 6s. Now, if the die was fair, mathematically we would expect 10. That's not what happened. On the other hand, we would be surprised if we got exactly 10 on everything, wouldn't we? We expect all those numbers to be sort of, quote, close to 10, but how do we define this idea of closeness? That's where, again, these rigorous black and white objective hypothesis testing techniques give us a way of answering that in a consistent way, so that, right, two researchers on two different sides of the planet are still going to come to the same conclusion regarding whether or not this die is fair. So let's see how we would actually go about doing that. Same 4-step hypothesis dance. Step 1, set up our hypotheses. Here our hypotheses are sort of a compound or composite, a little bit more complex what we've worked with. We have one variable, which is the outcome of a die. It has 6 categories, and so we have a conjectured probability distribution. 6 outcomes, 1, 2, 3, 4, 5, 6, and our hypothesis is that they're all equally likely, that they all have a probability of 1/6. The alternative is just the negation of that. The negation of that would be if at least one of these has a probability different than 1/6. Step 2, we construct our test statistic. Our test statistic takes a little bit of calculation, not as cumbersome as some of the other ones, like for instance our prediction interval calculations are much more cumbersome. Still, it's not something that's pretty to do by hand. The basic idea behind the test statistic is we look at each outcome. So the outcomes are we could roll a 1, a 2, a 3, a 4. And for every outcome, right, say for the outcome of rolling a 1, we can look at what we observed, that is how many 1s did we actually see rolled. I think there was 12 of them. And we could look at what we expected under the null hypothesis. Under the null hypothesis of a fair die, we would expect 10. So we look at that difference between 12 and 10, between what was actually rolled and what we expected to be rolled. We square that difference. We're used to doing that in statistics, right? Because sometimes we get more than expected, sometimes we get less than expected. If we added those differences up, we would get positives and negatives canceling. To avoid that, we look at the difference and we square it. So that part's very intuitive. For every outcome, we look at the difference between observed and expected, and we square that difference. That should be a little intuitive. What's maybe a little less intuitive is we take that squared difference for every outcome and we divide it by however many observations we expected to be there. So in this example, we're dividing it by 10. Why we do that's a little bit mathematical. It turns out that's important to actually derive a test statistic that has a known probability distribution. Now we do this process for every one of our outcomes, in this case for all 6 outcomes. We add those 6 numbers together and that gives us a test statistic. It follows a specific distribution, something referred to as a chi-square distribution. If you want to, just for fun on a Friday night, take a look a little bit more deeply at the calculations I'm talking about and all their sort of beautiful, rapturous detail. Feel free to take a look at our textbook. Once we've generated our test statistic, since we know its probability distribution, right? We said it's this enigmatic chi-squared distribution. We can use a computer or software program to look at probabilities, to generate p-values. The p-value is still essentially measuring the probability of seeing a sample as extreme as the one observed or more so, given the null hypothesis is true. So we're really sort of saying, this is not a perfect way of saying it, but I think it captures the spirit behind the p-value. And that is, we're really saying, or asking and answering the question, if this die was really fair, that's what the null hypothesis is saying, what is the probability of rolling what I just rolled? What's the probability of getting 12 1s and right all the other observations that we had? Once we have that p-value, of course, we can make our decision just like we always do. So let's actually look at how we might do this in our calculator. It's not too bad to do in the calculator. The first thing that we have to do, unlike a lot of our examples, this might be one of the first examples where we actually are putting data into the calculator. The easiest way to do that I've been able to find is to still start by hitting that stat button. Except instead of going over to tests, instead go to edit and hit enter. When you do that, it's going to bring up some lists that you can then fill in. So this is what it looks like after edit. The first list is our observed values. So we had 12 1s and 7 2s and 14 3s and 15 4s. The rightmost column is what we expect if the null hypothesis was true. There were 60 rolls. We expect 1/6 of 60. That is 1/6 times 60. That's 10 in every one of those categories. We need to communicate that information to our calculator. Once we've filled in our list, we hit stat again, and now we go over to tests. We go way, 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 way downtown, or if you're in the mood, you might instead go uptown, not nearly as far, and pick that. It's actually I wrote X, but it's the symbol chi, um, which is a Greek letter, and it's kind of like you'll see it's got a little bit of curvature to it that an X doesn't. So really it's saying chi square. It's the Greek letter chi, and it's an exponent, so it's actually chi squared. And then GOF, remember that was supposed to stand for goodness of fit test. And so there it is under our test menu. Apparently on my calculator it's option D, as in dog. May or may not be option D in your calculator. In fact, I've heard that some calculators don't even have it as an option, so you may have to install it on your calculator. If for some reason it's not on your calculator, feel free to let me know, and I'll help you figure out how to get it installed. When we select goodness of fit test, it asks us where the observed values are. The default is L1. That's where we put it. It says where you're expected. The default's L2. That DF is degrees of freedom. So the degrees of freedom are the number of outcomes minus 1. So our 6-sided die had 6 outcomes. The degrees of freedom are 6 minus 1, 5. The calculator actually filled that in by default. So I believe you can just leave the default there. And then we would cursor down to calculate and hit enter. And there's everything we need for a hypothesis test. We have our test statistic, which is 9.4. We have our p-value, which is 0.094. We'll look at our decision in the next slide, or slides. So our test statistic is 9.4. Our p-value is 0.094. That p-value is more than 0.05. So at least at the 0.05 significance level, we conclude there's not enough evidence to say that the probability of any outcome is different than 1/6. So to put that a little bit more plainly, we would conclude that this die appears fair, or at least there's not evidence that the die is unfair.